In recent years, the number of ships in service has increased, and larger ships have become more dominant. This has led to an increase in development of new ports in many parts of the world to allow ships to enter and leave, even those ports exposed to severe external forces or prohibited by the area to properly maneuver. Especially for a large ship, it is customary to have a pilot guided into and out of a port. But to ensure the ship's safe navigation at port, the ship's captain must visualize in advance how to steer the ship and be ready to compare it with the pilot's performance in his mind's eye. For safe navigation, the officer at the helm needs to have a clear understanding of external forces and surrounding conditions in order to berth and unberth the ship through cooperation with the tugboat operator. This requires the steering officer to be familiar with the performance, characteristics, and operation of tugboats. This DVD is intended for captains and deck officers whose duties include maneuvering of a ship to better understand not only the performance characteristics of tugboats, but also the correct use as an indispensable aid in berthing or unberthing of vessels. Tugboats are classified by their usage. Harbor tugs are intended to assist a large ship to enter and exit the port. Towing tugs to tow work vessels and other non-self-propelled ships, and salvage tugs to relieve ships in distress. This DVD focuses on harbor tugs. The propeller of a tugboat differs in type with its position of installation. A tugboat with its propeller toward the stern, like an ordinary merchant ship, has a number of different propellers available, including the conventional type propeller and a flat type rudder. A combined type with a conventional propeller and an added bow thruster. An azimuth stern drive, ASD type, using a quart nozzle type propeller with no rudder. And a pump jet type. On the other hand, a tugboat whose propeller is installed toward the bow is known as a tractor tug, which usually has a Voith-Schneider propeller or an azimuth propeller. The ASD-type propeller consists of a screw propeller and a surrounding quart nozzle, which enables the propeller to be turned in a full 360-degree range. Its distinct advantages from the conventional propeller include the ability to generate a strong thrust in any direction, forward, astern, left or right, and reducing the tugboat's overall length. The ASD type are manufactured under different names, such as duckpeller, Z-peller, or Rex-peller, but they do not significantly differ in working principle. In Japan, the ASD type propellers constitute the mainstream. The pump jet type propulsion system has a pump fitted to the hull bottom that spurts out seawater obliquely downward as a force to drive the boat ahead. By varying the spurt direction, the boat can be propelled in any direction in a 360-degree range. As its structure has a smaller projection from the hull bottom than a conventional flow toward the bow, accompanying the transverse shift and the pushing force of the tugboat together work in the direction of accelerating the turn. However, when the tugboat pushes the port side of the bow in the 3 o'clock direction, the force of the tugboat pushing the ship and the water flow toward the bow accompanying the transverse shift cancel each other to slow the turn. Hull movements can be considered in 2 separate aspects: force and turning moment. The following focuses on wind-induced hull movements. First, let us suppose that the wind is blowing in the direction of 45 degrees on the starboard of your ship. Wind pressure works on the ship's center of wind pressure. The wind pressures can be broken down into 3 elements, including the wind pressure in the longitudinal direction, wind pressure in the transverse direction, and wind pressure moment. On a graph of the longitudinal wind pressure coefficient, in which the horizontal axis represents the wind direction and the vertical axis represents the coefficient, it is negative at 45 degrees of wind direction. This means moving back. On a graph of the transverse wind pressure coefficient, in which the horizontal axis represents the wind direction and the vertical axis represents the coefficient, it is negative at 45 degrees of wind direction. This means being driven in the port direction. On a graph of the wind pressure moment, in which the horizontal axis represents the wind direction and the vertical axis represents the coefficient, it is positive at 45 degrees of wind direction. This means the generation of a clockwise moment. Overall, the ship turns clockwise while being driven obliquely port astern. Next, let us suppose that the wind is blowing in the direction of 90 degrees on the starboard of your ship, with the wind pressures in the longitudinal and transverse directions, and wind pressure moment same as before. A graph of the longitudinal wind pressure coefficient shows a slight positive value at 90 degrees of wind direction. This means slightly moving ahead. A graph of the transverse wind pressure coefficient shows a negative value at 90 degrees of wind direction. This means being driven in the port direction. A graph of the wind pressure moment shows a negative value at 90 degrees of wind direction. This means the generation of a counterclockwise moment. Overall, the ship turns counterclockwise while being driven obliquely port ahead. Now let us suppose that a Moss-type LNG carrier 300 meters between perpendiculars at halt is to be pressed sideways by four 4,000 horsepower tugboats. What will be the dynamic motions at work? For an ASD-type tugboat, the bollard pull, of which is calculated to be 1.5 tons per 100 horsepower, is at 4,000 horsepower, 60 tons. If 80% of this 60 tons can be used as thrust, the full thrust per boat will be roughly 48 tons. In a first case, let us suppose that a wind of 12 meters per second is blowing at the ship head-on, namely a relative wind direction of 0 degree. Regarding the ship's movement, both the wind pressure force and the pushing force of the tugboats should be taken into account. Usually, when the wind blows head-on, the wind force only works astern, but neither a transverse force nor a turning moment is generated. The magnitude of the wind pressure force then differs with the ship's shape and area exposed to wind. Here, supposing that the longitudinal wind pressure coefficient is minus 1.02 and the area of exposure to headwinds is 2,000 square meters, the longitudinal wind pressure is calculated to be about 18 tons. In order to move the ship exactly sideways from the start point of pushing, the tugboat's thrust should cancel the wind pressure force. The wind pressure force in the longitudinal direction is canceled by placing one of the tugboats for alongside towing or towing on a line at the bow and having it run at slow speed ahead in the 12 o'clock direction. The ship can be shifted transversely while adjusting the thrusts of the other tugboats. In a second case, suppose the wind is blowing directly sideways against starboard at 12 meters per second in a relative direction of 90 degrees. Same as before, both the wind pressure force and the pushing forces of the tugboats should be taken into consideration. Usually when the wind blows directly sideways, there are forces working ahead and transversely, causing a counterclockwise moment. Here, let us suppose that the longitudinal wind pressure coefficient is minus 0.02, the transverse wind pressure coefficient is minus 1.16, the wind pressure moment coefficient is minus 0.028, the area of exposure to headwinds is 2,000 square meters, and the area of exposure to sideway winds is 9,000 square meters. That would mean the forces working on the ship include a wind pressure in the longitudinal direction of about 0.4 ton on the bow, a wind pressure in the transverse direction of about 93 tons on the port side, and a turning moment of about 675 tons per meter counterclockwise. In order for your ship to shift from the start point of pushing in the exact transverse direction, the thrust of the tugboat should cancel the wind pressure force in the longitudinal direction and the turning moment. Furthermore, the pushing should be accomplished with a greater thrust than the wind pressure force in the transverse direction. It should be noted, however, that the wind pressure force in the longitudinal direction in this example is only 0.4 ton, which is too small for serious consideration. On the other hand, in order to cancel the turning moment, it is necessary for the tugboats toward the bow to have a greater thrust than the tugboats astern. For instance, if two tugboats each are to push your ship in the full 3 o'clock direction head-on 100 meters ahead of and 100 meters behind the center of gravity respectively, the combined thrust of the tugboats ahead should be about 7 tons greater than that of the tugboats astern. The combined thrust of the 4 tugboats in this case is about 192 tons, greater than the approximately 93 tons of the transverse wind pressure, and therefore transverse shifting is possible. Usually, when the ship is to be shifted transversely, an imbalance between the force of the tugboats ahead of the center of gravity and that of the tugboats behind would invite a turning movement, and accordingly, the power outputs of the tugboats should be adjusted appropriately. Regarding the turning of the supported ship, both the wind pressure force and the pushing forces of the tugboats should be considered as in the case of transverse shifting. Yet, unlike in transverse shifting, the change in relative wind direction with the ship's turning also deserves attention. If there is no other external force at work, the angular speed of turning is smaller in the early phase of turning and increases as turning progresses. Therefore, the ship is exposed to winds in the same direction for a long period of time in the early phase of turning. Here, let us suppose that a Moss-type LNG carrier at halt in ballast is to be turned 180 degrees starboard by 4 4,000 horsepower tugboats. The vessel measures 2,000 square meters in area of exposure to headwinds, 9,000 square meters in area of exposure to sideway winds, and 300 meters in length between perpendiculars. Shown here is a case in which the ship is turned 180 degrees by having 2 of the tugboats push the port side of its bow in the 3 o'clock direction, and the other 2 push the starboard side of the stern in the 9 o'clock direction, both at full power. The diagram to the left shows variations in wake when there is no wind, and to the right, wake variations when there is some wind. You can see that when there is no wind, there is substantially no shift ahead, astern, port, or starboard, and the turning takes place where the turn started. Next, when there is some wind, say 15 meters per second, directly at the bow, or at 0 degree in relative wind direction, the ship's position after the turn is behind where it was before making the turn because it has been driven astern. To adjust the turning position using only tugboats, a thrust against the wind would be needed. One way to achieve this is to have the tugboats ahead push in the 2 o'clock direction, and those astern push in the 10 o'clock direction, and maneuver the ship as if to have them push in the 3 and 9 o'clock positions respectively, with an increase in the turning angle speed. In the next case, there is a wind of 15 meters per second blowing in the exact transverse direction, 90 degrees in relative wind direction. The diagram to the right shows variations in wake when there is some wind. You will see that the ship's position after the turn is farther on the port side than before, as the wind has driven the hull in that direction. Adjusting the turning position using only tugboats would require a thrust in the starboard direction. In the early phase of turning, the stern would be pushed in the same direction as the wind, but the bow would have to be pushed against the wind. In one example of spinning, 2 tugboats at the bow are used at full speed, and the other 2 at the stern at slow speed. Therefore, it is imperative to take into account topological features of the surroundings as well as environmental conditions, and deploy the tugboats appropriately for these external factors. When the ship nears the port of call, the captain considers the port situation and the day's weather and decides how many tugboats will be needed. If the local association of pilots and/or the berth have their own tugboat requirements, the captain will also take these into account. If the ship has visited the port in the past, there should be no problem. But if it's its first call at the port, sufficient information to make a decision may not be available, and the captain will have to make a difficult choice. In view of this problem, this DVD will introduce the concept of tugboat power allowance. When the ship is to be berthed against offshore wind, pushing the ship by tugboats sideways involves two types of relevant forces, one to control turning by the wind, and the other purely required for transverse shifting. The force available for transverse shifting can be considered the balance of subtracting the force to control turning by the wind from the combined thrust of all the tugboats. The Tugboat Power Alliance indicates how much greater the force of tugboats available for transverse shifting is than the wind pressure force. It varies with the ship's load condition, the power output, number, and arranged position of the tugboats, and the wind direction and velocity. In reality, the arranged positions of tugboats to push or pull the ship at its bow and stern are substantially unchanged. Therefore, if you prepare a graph in advance for each of the relevant factors, including the ship's loaded condition, the thrust and number of the tugboats, and the wind direction and velocity, you can keep reference drawings available to always use aboard the ship. Now let us look at the steps in preparing the graph. For our example, one tugboat each is assigned to the bow and stern to help the ship berth against offshore wind. 1. Obtain data on the ship's wind pressure coefficient and area of exposure to sideway winds. 2. Calculate the turning moment and the transverse wind pressure force. Calculation formulas will be provided at the end for your supplementary reference. 3. Check with blueprints, including the general arrangement, to find out the distances from the center of gravity to the supposed working points of the tugboats. 4. Check the power output and bollard pull of each tugboat. If no such information is available, make them at 100 horsepower and 1.5 tons respectively. Accounting for the influence of waves, use an 80% towing power for your calculation. 5. Make your tugboat power allowance under the assumption that the tugboat responsible for turning against the wind pushes at full power. Or when the tugboat at the bow cancels the wind pressure moment, the relationship between the force, YT1, with which this tugboat pushes is full power, and the force, YT2, with which the tugboat at the stern pushes for transverse shifting in parallel is YT2 equals YT1 times L1 minus NW divided by L2. 6. The force available for use in transverse shifting is represented by Y F by T equals YT1 plus YT2. By dividing the force available for use in transverse shifting by the exact sideway wind pressure force, the tugboat power allowance can be calculated. Tm equals Y F by T divided by YW. As the tugboat power allowance can be calculated in this way, if you calculate the allowances at such intervals as every 10 degrees of relative wind direction and every 5 meters per second of wind velocity and make a graph with the data, you can readily determine the minimum number of tugboats needed under given conditions. The tugboat power allowance indicates how much greater the combined power of tugboats available for use in transverse shifting is than the wind pressure force. If wind direction and velocity is known before port entrance or port departure, securing a number of tugboats greater than the one in tugboat power allowance would be sufficient. However, experience tells us that the recommended tugboat power allowance should be 3 to 4. For a basic maneuvering pattern using tugboats, there is no significant difference between large and small ships. If requirements in the number of tugboats and their total power output are adequate, safe maneuvering can be accomplished. It is essential to keep in mind that external forces always vary, and therefore to secure more than enough tugboats to ensure safe maneuvering. Let's consider a fully loaded VLCC, for example. It is 310 meters long between perpendiculars and has a 1,100 square meter area of exposure to headwinds and a 3,200 square meter area of exposure to sideway winds. The distance between the tugboat and the ship's hull center, both on the bow side and on the stern side, is 150 meters, while the tugboat's bollard pull is 48 tons. In the graph, the horizontal axis represents the relative wind direction as seen from the bow. The vertical axis represents the tugboat power alliance, which is indicated by the red line when the wind velocity is 10 meters per second, by the green line when the wind velocity is 15 meters per second, and by the blue line when the wind velocity is 20 meters per second. To use the graph, with a recommended tugboat power alliance of 4, draw a horizontal line at that number. The number of tugboats indicated in the area above this horizontal line would be sufficient. For instance, if a 10 meter per second wind is blowing from a relative wind direction of 60 degrees, 2 tugboats would be sufficient because the tugboat power allowance represented by the red line is above this horizontal line. However, if the wind velocity rises to 15 meters per second with the wind direction unchanged, 2 tugboats would not be enough because the green line shows an area below the horizontal line. If there is a shortage of tugboats, successively check the pre-drawn graphs for 3 tugboats and 4 tugboats. If the relative wind direction is 60 degrees and the wind velocity is 15 meters per second, assign 1 tugboat to the bow and 2 to the stern. The tugboat capacity would then be sufficient. Next, let us look at the same VLCC in ballast. It is 310 meters long between perpendiculars and has a 1,800 square meter area of exposure to headwinds and a 7,100 square meter area of exposure to sideway winds. The distance between the tugboat and the ship's hull center, both on the bow side and on the stern side, is 150 meters, and the tugboat's bollard pull is 48 tons. If, for instance, a 10 meter per second wind is blowing in a relative wind direction of 60 degrees, 4 tugboats would be sufficient because the area is above the horizontal line. However, if the wind velocity rises to 15 meters per second with the wind direction unchanged, there would arise a shortage of tugboats because the green line shows an area below the horizontal line. In this case, for instance, 3 tugboats at the bow and 2 at the stern would be sufficient. Finally, let us look at a PCC in ballast, which has a large area exposed to wind forces. It is 190 meters long between perpendiculars and has a 990 square meter area of exposure to headwinds and a 5,750 square meter area exposure to sideway winds. The distance between the tugboat and the ship's hull center, both on the bow side and on the stern side, is 90 meters, and the tugboat's bollard pull is 48 tons. For instance, if a 10 meter per second wind is blowing in a relative wind direction of 60 degrees, 2 tugboats would not be sufficient because the tugboat power allowance represented by the red line is below the horizontal line. So far, it has been explained how to use the graph of tugboat power alliance, but it should be noted that the tugboat power allowance does not take into account the influences of tidal currents and shallow water. The previous section considered the tugboat power allowance only as it pertains to the influence of winds. Now let us look at how it is affected by tidal currents and water depth. When there is a current, the fluid pressure working on the ship increases with the exposed area under the waterline. For example, if there is a current with a velocity of 0.6 knot against the bow, 0 degree in relative direction, what is the fluid pressure on a fully loaded VLCC? For instance, the tanker is 300 meters long between perpendiculars and has a 6,000 square meter area under the waterline on the broadside, a 1,200 square meter area under the waterline at the bow, a 20-meter draft and a water depth draft ratio of 1.5. If the longitudinal fluid pressure coefficient is 0.04, the fluid pressure will be about 1 ton. Or if there is a current of 0.6 knot exactly sideways, 90 degrees in relative direction, and assuming a transverse fluid pressure coefficient of 1.6, the fluid pressure will be about 48 tons. As you can see, the hull shape is susceptible to the current in the transverse direction rather than at the fore and astern. In considering the required bollard pull, only transverse currents are taken into account to estimate the greatest possible effect. Now let's consider water depth. If water depth is less than about double the draft, the influence of shallow water will become significant, and this means a substantial difference in required tugboat power. This graph, based on the calculation by OCIMF, using the broadside area under the waterline and the water depth to draft ratio as parameters, gives you the required bollard pull. The fluid pressure transverse force coefficient is what is applied to a loaded tanker based on a seawater density of 1,025 kilograms per cubic meter. Looking at the graph for a ship with a 6,000 square meter broadside area under the waterline meets a current of 0.6 knot and its water depth to draft ratio is 1.5, you'll find point B directly below a given point A. Referring this point B to the portside axis, the required bollard pull at this current speed and water depth is about 60 tons. Required tugboat power is twice as great at a water depth to draft ratio of 1.1 than at 1.5. So far, we have explained the dynamics involving the use of tugboats for maneuvering a large ship that includes such motions as transverse shifting and turning in the aspects of forces and moment. However, in actual maneuvering, it is imperative the officer at the helm recognizes these actions as sequences and thinks about the next action to take in performing steering duties. Now let us see how maneuvering with the aid of tugboats is actually done. In our example, a large 260-meter class PCC enters port. First, we will outline the maneuver required to bring this vessel into port. The ship, having engaged tugboats near buoys number 1 and number 2 near the fairway entrance, and using both its main engine and the tugboats, approaches the berth while slowing down. As the turning basin is set in the circle position in the chart planned in the advance, the ship is once brought to a halt within the circle. With the docking side at the starboard, the PCC uses the tugboats and its own bow thruster to turn left. Its main engine and the tugboats drive it astern, bringing it to a halt once off the quay along which it is to be docked. Then, while the tugboats adjust the ship's transverse moving speed at no more than 10 centimeters per second, the PCC is slowly docked. We have seen the flow of the maneuver, but let us review the process, this time in more detail along with general caution regarding each step. In the approach phase, first the magnitude of external forces and the surrounding traffic are considered, and a decision is made on where to take up the tug lines, for instance, near buoy XX, and the tugboats are notified of this decision. On that occasion, the tugboats are also told of the positions on the supported ship to take the tug lines. In this case, a 3,500 horsepower